Here, they have provided us ID versus VD relationships for two of the diodes. We have to find which ID and VD characteristics belongs to which diode. First of all, if we observe, at particular, the cut-in voltage of first diode is very less when compared with second diode. And we know that for every Schottky barrier diode, the cut-in voltage is very less. So the characteristic number 1 belongs to Schottky diode. And second characteristics belongs to PN junction diode. And now we have to get, and third relationship belongs to which diode. If we can observe, for a particular VD, we know that for a Schottky barrier diode, the reverse saturation current is very high. So if we compare between these two characteristics, characteristic number 4 have more reverse saturation current. So number 4 represents Schottky barrier diode, whereas number 3 represents PN junction diode. So overall, 1 and 4 belongs to Schottky diodes and 2 and 3 belongs to silicon junction diode. So it's option B. In this question, we have to find voltage drop across 5 kilo ohms resistor for the given circuit shown here. First of all, step 1, let us determine whether this GNR diode is in on condition or in off condition. For finding that, let me open circuit the Zener diode and let me find the voltage across these two terminals. Let me say, let it be V. Now, in order to get V, we can apply voltage division rule. It is 100 into 10K divided by 15K Hz. And they have specified the Zener voltage to be 50 volts. So if we do this calculation, it's around 66 volts, 66.67 volts, which is greater than 50 volts. As Zener voltage is less than the obtained voltage, the Zener will be in on condition. So therefore, we can simplify the circuit as 5 kilo ohms, and here the voltage will be 50 volts and applied voltage is 100 volts and it is 50 volts. Now applying KVL in this loop, we get minus 100 plus voltage across 5 kilo ohms plus 50 equals to 0, which is nothing but voltage across 5 kilo ohms is 50 volts. So it's option B. In this question, they have provided this N-channel JFET and they have given this data for N-channel JFET. If we can observe, at VGS is equal to minus 4 volts, we have to find the drain current. For any JFET, we have the relationship for drain current as ID is equal to IDSS into 1 minus VGS by pinch off voltage whole square. Just plugging in the values, it is 20 milliamperes into 1 minus given VGS is minus 4 volts divided by pinch off voltage is minus 8 volts whole square, which is nothing but 20 milli into 1 by 4. It is nothing but 5 milliamperes. So at VGS is equal to minus 4 volts, our drain current turns out to be 5 milliamperes. Again, they have asked us the transconductance parameter also. We know transconductance is nothing but maximum transconductance into 1 minus VGS by VP. They have given GM0 value also. It is nothing but find the transconductance. So I am plugging in as minus 4 and it is minus 8. Here they have provided us FET transistor along with some parameters. That is nothing but they have provided current through drain terminal is 5 milliamperes and they have asked to find us VDS and VGS. So as same drain current passes through this source resistor, let me assume voltage at this terminal to be Vs. So from that Vs can be written as ID into Rs. ID is nothing but 5 milliamperes and Rs is 500 ohms. Turns out to be 2.5 volts. So voltage at source terminal is 2.5 volts. Now as this is drain terminal, let me assume voltage at this drain terminal to be Vd. In order to find Vd, let me write KVL in this path. Writing KVL minus 10 plus ID RD plus voltage at drain terminal equals to 0. That is nothing but ID is 5 milliamperes and RD is 1 kilo ohm plus VD equals to 0. This turns out to be VD is 5 volts. Now we have to find VDS. VDS is nothing but VD minus Vs. Voltage at drain terminal is 5 volts and voltage at source terminal is 2.5 volts. It is nothing but 2.5 volts. So VDS is 2.5 volts. Again, we have to find VGS. VGS is nothing but VG minus Vs. To find voltage at gate terminal, as no current passes through the gate terminal of this FET transistor, we can treat as 0 minus voltage at source terminal is 2.5 volts. So it is minus 2.5 volts. VGS is minus 2.5 volts and VDS is 2.5 volts. in this question, they have provided us the data as alpha is 0.97 for a fixed bias circuit, and at temperature at 30 degrees, IC is 2.2 milliamperes, and at 60 degrees, it is 3.8 milliamperes. They have provided us the reverse saturation current changes 1.7 microamperes per every 1 degree change in temperature. So we have to find the stability factor. We know that current stability factor is given by change in collector current to change in reverse saturation current. For a temperature change of 30 degrees, first of all, let us find delta IC naught for change in 30 degrees. We can see for 1 degree centigrade, it is 1.7 microamperes. For 30 degrees centigrade change, it is 1.7 microamperes into 30, which is nothing but 5.1 microamperes. It's 51 microamperes. So we have obtained the denominator. Let us find change in IC for the same change in 30 degrees centigrade. For change in 30 degrees centigrade, change in IC is nothing but 3.8 minus 2.2 milliamperes, which is nothing but 1.6 milliamperes. So plugging in these values in the stability factors formula is 1.6 milliamperes divided by 51 microamperes, and it turns out to be 31.3. So this is our required answer. So it's option C. In this question, they have provided us as an intrinsic silicon crystal, and we have to find the amount of impurity atoms that we should add in order to create the complete crystal to have a resistivity of 10 power minus 4 ohm meter. We know that conductivity of extrinsic semiconductor is nothing but Nd Un into Q, and we have to find the amount of donor atoms that we should add to get the resistivity of 10 power minus 4 meters. We know that conductivity is nothing but 1 by resistivity, Nd Un into Q, which implies Nd is equal to rho into Un into Q, which is nothing but 10 power minus 4 into, given the mobility of electrons as 0.138, to charge of electron is 1.6 into 10 power minus 19. Just in this question, we have to find this value. For finding such kind of values, just go through the options. We have 10 power 23 in the numerator. If we can see, 10 power 19 minus 19 and 10 power minus 4 makes us 10 power 23. Again, as we are not provided with calculator in our exam, so we have to find the value of 1 by 0.138 into 1.6. Now, let me show you how to find such kind of values in your exam. Let me approximate 0.138 as 0.14 into, it is 1.6. So we can write 0.14 as 14 by 100 into 1.6 as 16 by 10. It is nothing but 1000 by 14 16, sir, it's 224. So if you can see this value, it is obviously less than 5, slightly less than 5. If we can see the options, the option C, which is slightly less than 5, which is nothing but 4.528, we can choose it as option C, because If we go with option A, it is far less than 5. If we go with option B, it's 2.5. It's also far less than 5. If we go with option D, it's greater than 5. So we cannot choose option D. So in this kind of questions, getting the value of these decimals plays an important role in your exam. So go with some approximations and you can choose the answer with the help of given options. So it's option C. For a P plus N junction diode, they have given the built-in potential as 0.8 volts, and at a reverse bias of 1.2 volts, we have a width of depletion region as 2 micrometers, and if we increase the reverse bias voltage to 16.2 volts, we have to find width of this depletion region. From this figure, you can observe that P plus is heavily doped and N is normally doped. We know the relationship like width of depletion region will be extended more into the lightly doped region. So the N region has more depletion width when compared with P plus region. And also we know the width of depletion region is directly proportional to built-in potential plus applied reverse bias voltage. For the second case, that is, if we can apply the reverse bias as 16.2 volts, let me denote it as W2 to the first case, that is at reverse bias voltage of 1.2 volts, can be written as square root of VB is constant plus VR2 divided by VBI plus VR1. If we can plug in the values from that table, built-in potential is 0.8 plus reverse bias second voltage is 16.2 volts divided by built-in potential is 0.8 plus applied first reverse bias is 1.2 volts, which is nothing but it is 17 by it is 2. Here comes the calculation part. If we can approximate this 17 as 18, we get the square root value is 3, which is nothing but W2 by W1. But in the first case, at 1.2 volts, they have given width of depletion region to be 2 microamperes. So, into 3 from this relationship. Width at first reverse bias voltage is 2 and it is 3, which is nothing but 6 micrometers. So, width of our depletion region at a reverse bias voltage of 16.2 volts is 6 micrometers. So it's option C. Here, they have arranged two diodes in parallel. One is made up of germanium and other is made up of silicon, and they asked us to find the value of V0 in this from this circuit. And we know that whenever two diodes are placed in parallel, which diode has the least cut-in voltage, that will be on first. So, as germanium diode has 0.3 cut-in voltage and silicon diode has 0.7 volts, germanium diode will be on first. and silicon diode never goes into on state. So we can replace it as 0.3 volts, and as silicon diode is not in on condition at any point of time, we can replace that with open circuit. So we have to find V0. If we can apply KVL in this path, we will get the value of V0. Applying KVL, we get minus 10 plus 0.3 plus V0 equals to 0. So V0 is 9.7 volts. So it's option B. In this question, they have given two samples of crystals. One is sample A, and it is doped with boron of 10 power 18 atoms per centimeter cube. We know that boron is a third group element, so we can treat it as acceptor impurity. So I denoted it with Na, which is nothing but 10 power 18 atoms per centimeter cube. Now again, sample B is doped with phosphorus atom. We know that phosphorus is a fifth group element, so it can be treated as a donor impurity. So I have denoted that with Nd. It is also doped with 10 power 18 atoms per centimeter cube. And they have provided us mobility of electron to mobility of hole ratio as 3, and they have asked to find us conductivity of sample A to conductivity of sample B. From here, this is a p-type semiconductor. Conductivity of p-type semiconductor can be approximately given as Na mu p into Q. This is sample A conductivity. Sample B can be treated as n-type semiconductor. So for n-type semiconductor, conductivity can be approximately given as donor impurity concentration into mobility of electrons into Q. They have asked us to find conductivity of A to conductivity of B. We can write Na mu p to Q by Nd Un to Q, which is nothing but Na to Nd to mu p by mu n. Na and Nd are same, so those ratio will be 1. And they have provided electron to hole mobility as 3, but here hole to electron mobility is 1 by 3. So required answer, that is conductivity of sample A to conductivity of sample B, is 1 by 3. So it's option B. This question, they have doubled the parameter W by L ratio of N-channel MOSFET, and they have asked a new transconductance that is obtained by doubling W by L ratio of MOSFET. First of all, let us write some current equations for MOSFET in saturation. That is nothing but UN Cox W by L divided by 2 into VGS minus VT whole square. They have asked us to find the transconductance parameter. Transconductance can be defined as variation in drain current with respect to VGS. So now differentiating this equation with respect to VGS, we obtain 2 into mu n Cox W by L by 2 into VGS minus VT. Cancelling these two, we get transconductance as mu n Cox W by L to VGS minus VT. From this relationship, we can write VGS minus VT as 2ID divided by mu n under root. Now, substituting this VGS minus VT value for Cox W by we obtain transconductance as square root of 2ID into mu n Cox W by L. From this relationship, maintaining constant current, and if we double W by L parameter, transconductance of 2 by transconductance of 1, maintaining same constant ID current and same mobility and Cox parameters, it is W by L. It is nothing but we have double the W by L parameter. So it is nothing but root 2 times of initial transconductance value. So it is root 2 times of transconductance of first parameter. So it's option D.